Hi everyone. In this video I'll be talking about 3.4 and 3.5. I'm going to save 3.6 for a different video. So as I've been emphasizing, the derivative is very, very similar in definition, and in many cases it's exactly the same as thinking of the slope. So when you think derivative, you can kind of think slope interchangeably. So if you look here, we have derivatives as rates of change. So AROC just simply means average rate of change. So this is what we've been doing, right? Here's our slope formula, the change in y over the change in x. And we're now calling that the derivative, right, y prime, because we're applying a limit in which that change of x vanishes, right? That change of x goes to 0. In other words, we're turning this average into an instantaneous. Okay, so the derivative helps us do that. Here is a position function. So also something I've been trying to emphasize is that if you are given a position function and then you take the derivative, then you will now have a velocity function. If you take another derivative, you will have an acceleration function. That's if you're given a position, like a change in distance per change in time. Okay? So it says the position of a particle is given by this equation. It's this cubic equation involving t. Part 1 says find the velocity at time t. What is the velocity after 1 second? Okay. So part 1, it says find the velocity at time t. So the velocity, as I said, we're given a position function. So I need to take one derivative and I'll have a velocity function. So f prime of t will be, by the power rule, the 3 comes down and we reduce the power by 1. So 3t squared minus 16t plus 24. So this would be the velocity at time t. And then it went on to ask for what is the velocity after 1 second. So to actually evaluate this now, I would do f prime of 1. So 3 times 1 squared minus 16 times 1 plus 24. So let's see what this is. Looks like 11. And it didn't say what our units were, like meters or feet. I don't think so. I'm just going to say like some units per some seconds. Okay. So that's the other part of part 1. So part 2, when is the particle at rest? So if you think about this conceptually, you are at rest when your velocity is 0, right? So for part 2, we're going to work with the velocity function. So we need to look for, maybe I'll do this in red, but we need to see when f prime of t equals 0. That'll be when the particle is at rest. So we had f prime of t right here. And solving this, we can use the quadratic formula. So t would be 16 plus and minus the square root of negative 16 squared minus 4 times 3 times 24 all over 2 times 3. So I'll go ahead and type that in. Hopefully you guys can see that, sorry. The calculator, I mean. So 16 plus, and then it'll be the same as positive 16 squared, so I'll just write it that way. Minus 4 times 3 times 24, 2 times 3. I got a math error. So it looks like that discriminant. So just looking at the radicand, right, the discriminant of this quadratic formula, if you look at 16 squared minus 4 times 3 times 24, that's a negative number. So there's a negative number inside of this square root, which means that this is imaginary, which is math's way of saying that this never equals 0 within the real number system. So within real time, which is what we're talking about, this thing never equals 0. So when is the particle at rest? Never. Okay, so the fact that this is imaginary is the math's way of saying, hey, that thing that you're wondering happens, it doesn't happen. All right, so part 3. When is the particle moving in the positive direction? State this in interval notation. So when is it moving in the positive direction? So for positive direction, what we think of conceptually is a positive velocity, because velocity is not just how fast you're going, it's also in what direction you're going. So when velocity is negative, that means you're using some speed in the negative direction. When velocity is positive, that means you're using some speed in the positive direction. Okay, so if we're wondering when it's moving in the positive direction, then we're really wondering when f prime of t is greater than 0. So in other words, when 3t squared minus 16t plus 24 is greater than 0. And what we just found is that it never equals 0, actually. And it actually never goes negative. Another way of seeing that would be to find the vertex of this quadratic. Please note that it's opening up, right? And the vertex would be positive. So in other words, this thing is always greater than 0. So in interval notation, this thing is always moving positively. So from 0 to infinity. In other words, it's always moving in the positive direction. So that's part 3. Part 4, find the total distance traveled during the first 6 seconds. So this thing never turns around. And even if you turn around, we need to count that as distance traveled, but this thing never turns around. So for the distance part, we simply need to take f of 6 minus f of 0. So plugging that in, maybe I'll use a different color just to make it a little more obvious. So I'm plugging in 6, and then I'm plugging in 0, and I'm subtracting those, right? Because I'm using the position function to say, hey, where are you at 6 seconds? And then where are you at 0 seconds? And then I'm going to subtract those to find the total distance. Okay. So this would be plugging in 6, so 6 cubed minus 8 times 6 squared plus 24 times 6 minus, if you plug in 0 to our given function, you're just going to get 0. So I'm just going to say 0. And if you calculate that out, that'll be 72 units of some kind. I don't know if it's feet or meters or light years, but some linear unit. Okay, on to part 5. Let's see what it says. So it says draw a diagram like figure 3.24 on page 270 in the book to illustrate the motion of the particle. Okay. So part 5. We basically have a particle that starts moving in the positive direction, and then that's it. That's all we know about it. So for the first 6 seconds, maybe I'll draw this thing. So here's 0 seconds, and we have some particle here. And then it begins to move this direction. In the positive direction, that is. Let's just identify that it is here after 6 seconds. And that this is 72 distance units there. So it's here after that 6 seconds. Okay. Really, it would just continue. So. All right, so on to part 6. It looks like I'm running out of paper. 1 second. So part 6, it says find the acceleration at time t. So similar to part 1, actually. Sorry about that. So the acceleration would just be the second derivative of the position function. Right, so we had oops, it's part 6. We had a position function of f of t equals t cubed, t squared, plus 24t. And then that gave us a velocity function. I'm just recapping. So if I want an acceleration function, which is what we want here, then I just need to take the derivative of the velocity function. So f double prime of t, 6t minus 16, it looks like. What is the acceleration after 1 second? So I'll just go ahead and box this for part of my answer, and then f double prime of 1. So that would be -10, and then that would be some distance unit per second squared. So negative acceleration at that point, in other words, slowing down. Everyone, so I typed in, you can see in blue, I typed in the original function. I had to use x. Desmos doesn't like t's. So I typed in blue, hopefully you can see, is this top one here. Is our original function. Okay, so that blue one, hopefully you can tell the color, is our original function. Then we have the green as our first derivative, meaning the velocity. And then the purple one here is the linear function, which is the acceleration. So for part 7, it said graph the position function, the velocity, and the acceleration, all from 0 to 6 only. So what you can do in Desmos is, rather than just type in the function, so if I type that down here, then you'll obviously get the entire function, right? If you want to restrict it, like what was said in this problem, just from 0 to 6, you can use this notation. You can use this set, and then this is saying, hey, only graph this following function between, or whatever numbers you want, right? And in this case, 0 to 6. So I did all of them that way. So, and yeah, if I want to zoom in or kind of get a different view of it, I can change my y-axes to things that are a little more reasonable, just with respect to the graph, right? So I can see the nature of the thing a little better. So maybe I'll just go from x just to 7 or something like that. And I don't need to go all the way to -6. So this looks better. So you can see the velocity, right? As this position is increasing, we're getting away from our starting point. So you can imagine something essentially moving along this axis. That's what this blue line means. Something is not moving along this blue line. Let's be clear about that, okay? Something is simply moving along this axis, and we're plotting the time along this axis. We're not plotting horizontal position here. We just have 1D, and we know a time dimension as well. So we just have a thing moving in a line, okay? And so it begins fast, and then it slows down. And that's what this curvature means here. And then it begins to speed up again at this end here. So here's the velocity going down, reaching a minimum right around here, right? Here's the velocity at a minimum, the green one. And then it begins to speed up again, right? As this particle is on this axis, speeding up again based on this curvature. But let's be clear, there is not a particle moving in this curve here. We only have one dimension of kind of physical information. For the purple one, if you look at the acceleration, which would be described by the purple one, it's first negative. You can see it's down below 0. So all this is negative acceleration, which means this is all slowing down, which is also another way of saying velocity lessening, right? Here's negative acceleration, meaning slowing down, and then it crosses 0. That's a point at which a minimum of the velocity was reached, and then it goes positive, right? Positive acceleration means speeding up. Back to 3.5. Hi everyone. All right, welcome back. 3.5, derivatives of trigonometric functions. So interestingly, I've been encouraging you guys to think about slopes of tangent lines when you look at a curve and thinking about its derivative. So yeah, trigonometry is going to come back in a big way in this calculus class. It's going to be a challenge if your trigonometry is a bit rusty, but it's an opportunity for you to improve your trigonometry. But if you're aware that your trig, needs a little work, then just be aware you might need to invest some extra time in this class because there is going to be trigonometry here. So we have a couple graphs. Looking at them, we have a sine curve, and then what is being said below it is simply that this curve is a graph of this sine curve's derivative. Okay, and let's see if we can figure out why. So these lines are meant to be slopes of little example tangent lines, right? Just a few of infinitely many options. So all these little marks, hopefully you can see that in your notes. These are meant to be little example tangent lines. So if you check this one out, just this one right here at 0, if this is its derivative, then this graph will be a catalog of all the slopes of tangent lines to this curve. So what this is saying is, okay, here's a tangent line. This is the value of the slope of that tangent line, right at 0. Check out this tangent line right here at pi over 2. It appears to be horizontal. And what do we have here at pi over 2? We have 0 because that is the value of this horizontal tangent line, right at 0. Over here at pi, right, sine of pi is 0, so we're right here again. But the tangent line, specifically at pi, of sine, appears now to be negative, right? Here's the slope of this tangent line appears to be negative. And right down here at pi, here's a negative value. So indeed, this curve is a list of all the slopes of tangent lines to this curve. But the point is, what curve does this remind you of? So what curve does this remind you of? This one is sine. This one looks very, very similar to cosine, and it is indeed exactly cosine. So interestingly, the derivative of sine is exactly cosine. All right. So let's see. Now knowing that, if I want to take a derivative of a function now involving a trigonometric function, if it involves sine, I'm good to go. We'll need to talk about the derivatives of other ones, like what about the derivative of cosine or the derivative of a tangent or anything else. So f prime of x, I'm taking this function's derivative. So this is just our same old power rule here, so 3x squared. But then this function obeys this rule, right, which we just saw from the graphs. So I'd have plus 3 cosine of x as the derivative, right? The 3 just gets attached. I can move the derivative operator past the constant and just work on the sine function. I'll leave example 5 for you to try, but I'll let you know you need the chain rule. Sorry, not the chain rule, but the product rule for this one. Chain rule is coming in the next section. Okay, on the next page, 42. Yeah, if you do a similar investigative look, like if you graph cosine, check this out. So if you graph cosine, you can begin to look at the tangent lines for its curve. If you do that, then it's not as simple as just being sine. So if you graph all the slopes of these tangent lines, right, if you do a similar investigative thing here for cosine rather than sine, like look at the slope of this tangent line, for instance, and so on, and then plot all those values, what you'll get is actually negative sine. Not exactly sine, but negative sine. Okay, so just know that. Example 6 says, if f of x is tangent of x, find f prime of x. So I haven't told you what the derivative of tangent is, but I have spoken of what the derivative of sine and cosine are. So if we rewrite tangent in terms of sine over cosine, then I can use the quotient rule and figure out a formula for the derivative of tangent. So if we have f of x equals sine of x over cosine of x, which is the same as tangent from trigonometry, then f prime would require the quotient rule. Just real quick, if we have f over g and we want to differentiate low d high minus high d low, square the bottom, and away you go. All right, so g, so cosine, so I'll just write it. Cosine of x, right? I'm following this formula now. So the one that's on the bottom is cosine, so I'm just writing it, and then I need to write whatever I think the derivative of sine is. I need to write what the derivative of sine is. So that derivative is cosine. Okay, so here's g times f prime, in other words, in terms of this. Kind of confusing because I have f prime over here. But for this is f prime. Minus whatever's on the top, right? F, just f, as is. And then times g prime. G prime is cosine. Sorry, g prime is negative sine because g is cosine. So negative sine, and I'm multiplying. And then all over cosine squared of x, right? Just the bottom squared. So I'll actually carry out these multiplications. So f prime of x would then be cosine squared x plus really sine squared x over cosine squared x. From the Pythagorean identities from trig, we have 1 here. So this would be 1 over cosine squared x. 1 over cosine squared is the same as secant squared x. And that is the derivative formula for tangent that you can actually just use from now on. You don't need to derive the formula every time, of course. All right, but you could. If you forget, you could, as long as you remember the derivative formulas for sine and cosine. So here's a bunch of trig derivative formulas. Yeah, you need to know these. Notice the derivative of anything that begins with the letter C is negative. Okay, that might help. Example 7. Find an equation of the tangent line to this curve. So we have y equals 2x sine x. Specifically at this point, pi over 2 and pi. So I would need that this point is on the curve. And I believe it is, right? If you plug in pi over 2, the 2's cancel, you just get pi. And then sine of pi over 2 is 1, so you have pi times 1 is pi. So that point looks good. So for the slope of this tangent line, we'll need to take the derivative of the curve and then plug in our x. That'll be our slope. So let me find y prime. For y prime, I need the product rule. So derivative of the first times the second unchanged. Just to remind us of that, if you're taking the derivative of a product, you can take the derivative of the first times the second unchanged plus the first unchanged times the derivative of the second. So y prime, derivative of the first unchanged would just be 2, and then times the second, so 2 times sine of x, plus 2x, right, just f as is, times the derivative of g, which is sine, so times cosine. So simplifying, we have 2 sine of x plus 2x cosine x. So this is a formula for the slope of any tangent line we want, but we're specifically interested in the slope of the tangent line at this x location here. So a notation we sometimes use is here's the derivative, and then I'm going to allow x to equal pi over 2 within that derivative. So that's a notation. It's kind of like y prime of. It's kind of like function notation. So 2 sine pi over 2 plus 2 pi over 2 cosine pi over 2. Sine of pi over 2 is 1. So this will be 2 times 1. This will be pi times 0. So this is all we have for the slope, right? This is the slope. Derivative is slope. So this is the slope we're going to use. So I can say y minus pi equals 2 times x minus pi over 2. That would be the point slope version of the line. Then if you simplify that into slope intercept, it's actually kind of nice. You just have y equals 2x. So to get a visual of this problem, I'll go to Desmos now. All right, stand by for that. All right, I wanted to show Desmos in regard to example 7 on page 42. So we had this original curve, y equals 2x sine x. Whoa. And then we had this given point. So pi over 2 and pi. And let's see, I'll go ahead and label that, I guess. And the problem was to find an equation of a tangent line to that curve specifically at that point. So we're looking for basically the equation of the line that's defined by my ruler, the left edge of my ruler there. Right? And just as a check, I'm going to type in the line that we got. I'll type it in slope-intercept form. There it is. So it's not that a tangent line has to just hit exactly once, right? So it's not a violation that it's crossing here. It's a tangent line just needs to share the slope of the curve at the point. All right. By the way, if you want to change to pi, you can. So over here, instead of the just normal numerical steps, you can say make the steps pi, and you can kind of have a better trig graph there. All right, talk to you all next time. Bye-bye.